Moving on to the polyatomic ions. Here is a table showing commonly encountered polyatomic ions. We can see from this table that the polyatomic anions far outnumber the polyatomic cations. So in this table, we have the formula, the common name of the ions, the IUPAC name, the charge, the valency, and the examples of compounds of such ions. You are strongly advised to be conversant with the formula and names of the ions in this table, as a fingertip knowledge of these is crucial to not just writing the formula of inorganic compounds, but also mastering the basics of chemistry. Now let's practice some of the ions we saw in the table. The first one should be ammonium ion. It has the formula NH4+. The IUPAC name is the same thing as the common name, which is ammonium ion. The charge of ammonium ion is +1 and the valency is 1. A typical compound of ammonium is ammonium chloride when it combines with the chloride ion. Another polyatomic cation that was not shown in the table is the hydronium ion. The hydronium ion has the formula H3O+. It is otherwise known as hydroxonium ion. Its IUPAC name is the same thing as the common name. It has a charge similar to that of ammonium ion, which is +1, and a valency of 1. Hydroxonium ion is usually an intermediate, that is a radical, that is found in acid-base reactions occurring in an aqueous medium. It is formed from the protonation of a water molecule. Moving onwards, we look at the acetate ion. The acetate ion has the formula CH3COO-, and its IUPAC name is actually ethanoate ion. It has a charge of -1 and a valency of 1. A typical compound of ethanoate ion is sodium ethanoate, that is CH3COO-Na. Number 4, we can look at the nitrate ion. The nitrate ion has a formula of NO3-. Its IUPAC name is actually trioxynitrate 5 ion. It has a charge of -1, a valency of 1, and a typical example of this compound is the nitric acid or the trioxynitrate 5 acid. Our fifth example would be a sister ion of the trioxynitrate 5 ion, which is the nitrite ion. The nitrite ion is just one oxygen atom less than the nitrate ion. So in this case, it is NO2-. Its IUPAC name is dioxynitrate 3 ion. It has a charge of -1, a valency of 1, and a typical example is the dioxynitrate 3 acid. Sixth example would be the sulfate ion. The sulfate ion is SO4-2-. Its IUPAC name is actually tetraoxosulfate 6 ion. It has a charge of -2, a valency of 2, and a typical example of this compound is sodium tetraoxosulfate 6, Na2SO4. Now, a sister compound, just like we saw in the case of the nitrate ion, is the sulfite ion. And like you easily guessed, the sulfite ion is just one oxygen atom lesser than the sulfate ion. So in this case, it's going to be SO3-2-. Its IUPAC name is trioxosulfate 4 ion. It has a charge of -2 and a valency of 2. And a typical compound is sodium trioxosulfate 4 ion. Another example is the carbonate ion, CO3-2-. The IUPAC name is trioxocarbonate 4 ion. It has a charge of -2, a valency of 2. And a typical example of this compound is the trioxocarbonate 4 acid, H2CO3. Looking at further examples, we'll check the hydroxide ion, which is OH-. The IUPAC name is the same thing as hydroxide ion. The charge is -1, the valency is 1, and a typical example of this compound is sodium hydroxide. Now, going further, we look at the phosphate ion. It has a formula of PO4-3-. The IUPAC name is actually tetraoxophosphate 5 ion. It has a charge of -3 and a valency of 3. And a typical example of this compound is a sister compound to this is the phosphate ion, PO3-. The IUPAC name is trioxophosphate 3 ion. So it has a charge of -3 and a valency of 3. Then we move on to the chromate ion. The chromate ion is CrO4 2-. It has a IUPAC name of tetraoxochromate 6, a charge of -2 and a valency of 2. Similar to this is the dichromate ion. The di here signifies that there are 2 chromium atoms in this. So we have Cr2O7 2-. It has a IUPAC name of heptaoxodichromate 6, a charge of -2 and a valency of 2. Our next example, we look at the cyanide ion. That is the Cn-. The IUPAC name is same thing, cyanide ion. It has a charge of -1 and a valency of 1. Similar to it is the cyanate ion. The difference between the cyanide ion and the cyanate ion is oxygen, OCN-. The IUPAC name for this cyanate ion is actually oxocyanate ion. It also has a charge of -1 and a valency of 1. When this oxygen atom in the cyanate ion is replaced by sulfur, it is called the thiocyanate ion. That's the same thing for the IUPAC name, the thiocyanate ion. We're going to put a stop to it for the examples. You can practice them as much as possible to get conversant with all the polyatomic cations and anions. This will go a long way in helping you in chemistry. There are few salient points from the table of polyatomic ions that we just studied that require explanation in order to aid better understanding of the topic of discussion. The first difference is between the prefix di and bi in the nomenclature of these inorganic ions. Starting off with di, let's use the chromate ion and the dichromate ion as our example. Remember we mentioned that chromate ion is CrO4 2-, while the dichromate ion is Cr2O7 2-. Anytime you see the prefix di in the name of an ion, what this simply means is that there are 2 atoms of the element in question present within the polyatomic ion. So in chromate ion, you see that there is just 1 chromium atom, while in dichromate ion, there are 2 chromium atoms. That is why the word di is present. Other examples of this include carbonic acid, H2CO3, otherwise known as dihydrogen carbonate, and dihydrogen phosphate. In these two, we can see that the prefix di is also present, and it implies that there are 2 hydrogen atoms within the molecule of these 2 compounds. On the other hand, the prefix bi means that one of the hydrogen atom within a molecule or ion has been replaced, usually by a metal ion. Or it can be simply defined that the ion in question contains a replaceable hydrogen atom. Take for example, in this carbonic acid, if one of the hydrogen atoms is replaced, it becomes HCO3-. And this HCO3-, we've already seen here that it is called bicarbonate ion. So what the bi here imply is that one of the hydrogen atoms from carbonic acid has been replaced, thereby remaining just 1 more, or that the 1 hydrogen present can still be further replaced. Similarly, in dihydrogen phosphate, if one of the hydrogen atoms is replaced, we have HbO4 2-. You'll be wondering, where did these 2 come from? A quick explanation is that the dihydrogen phosphate came from the phosphate ion. Once you add a single hydrogen atom to phosphate ion, it becomes HbO4 2-. The single hydrogen atom takes a single negative charge away from the phosphate ion. If you add 2 hydrogen atoms, it becomes H2PO4-. While if you add the 3rd hydrogen atom, it becomes H3PO4 without any negative charge. So back to the question, if a single hydrogen atom is taken away from dihydrogen phosphate, we get HbO4 2-, and this is called biphosphate ion. Of course, the bi implies that a hydrogen atom has been replaced. So I hope this clarifies the difference between bi and di in the nomenclature of inorganic ions. It just occurred to me that I made a mistake while explaining the difference between di and bi in the nomenclature of inorganic anions. The particular point of mistake came when I was trying to explain the dihydrogen phosphate ion. I forgot to indicate that the dihydrogen phosphate has a negative charge, as you can see here. So as a form of recap, we have phosphate ion, which is PO4 3-. If you add a hydrogen atom to phosphate ion, we have HPO4 2-. That is the biphosphate. If you add another hydrogen atom, you have H2PO4-, and that is the dihydrogen phosphate. And lastly, if you add the third hydrogen atom, you have H3PO4 without a negative charge. Now it is neutral. H3PO4 is actually known as phosphoric acid. So I hope that clarifies the misdemeanor. Next, we look at the difference between the suffix -ate and -ite within the names of ions. For a polyatomic anion that has two ions both involving the oxygen atom, the anion with more oxygen atoms will have the suffix -ate, while the anion with fewer oxygen atoms will have the suffix -ite. There are several examples to this, which are nitrate and nitrite, phosphate and phosphite, sulfate and sulfite, and lastly, chlorate and chlorite. So as we can see here, nitrate has 3 oxygen atoms, while nitrite has 2 oxygen atoms. That is, nitrite has 1 oxygen atom less than nitrate. That is why nitrite is taking the suffix -ite, while nitrate has -ate as its suffix, because it has more oxygen atom than nitrite. So the same thing applies to phosphate. Phosphate has 4 oxygen atoms, while phosphite has 3 oxygen atoms, 1 oxygen atom lesser than phosphate. Sulfate has 4 oxygen atoms, while sulfite has 3 oxygen atoms, the one with the lesser oxygen atom. The same thing applies to chlorate and chlorite. Chlorite has 2 oxygen atoms and chlorate has 3 oxygen atoms. That is, chlorate has 1 oxygen atom more than chlorite. In a situation where an element has more than 2 polyatomic ions involving oxygen, such as the halogens, in this case, we use chlorine. We can see here that chlorine has 4 polyatomic ions involving oxygen, viz. ClO3-, ClO2-. We have also ClO4-, and lastly ClO-. We've already seen earlier that ClO3- is the chlorate ion, while ClO2- is the chlorite ion. The rule states that the polyatomic ion with 1 oxygen atom more than the anion with the suffix -ate, that is, the polyatomic ion with more oxygen atom than chlorate in this case, is given the prefix par. So ClO4- is going to become perchlorate, while the polyatomic anion with 1 oxygen atom less than the anion with the suffix -ite, in this case, the anion with more oxygen atom than chlorite, is going to be given the prefix hypo. So ClO- is going to have the name hypochlorite. To reiterate, perchlorate is given the name per because it has 1 oxygen atom more than chlorate, while ClO- is given the name hypochlorite because it has 1 oxygen atom less than the anion chlorite. It is worthy of note that hypochlorite is the active ingredient responsible for the cleaning agent of bleach. Liquid bleach contains NaClO, that's sodium hypochlorite, which dissociates in solution to give Na+, then ClO-. The ClO- is responsible for the cleaning action on clothes during laundry. That is why NaClO, sodium hypochlorite, is commonly called liquid bleach. The hypochlorite ion is also found in bleaching powder, which is actually calcium hypochlorite. As a form of general knowledge, there is a bleaching agent in our country. The name of the product is Hypo, and one would wonder that most likely the name of this bleaching agent must have been gotten from the active ingredient in bleach, which is hypochlorite ion. Proceeding to the next fact that can be deduced from this table. When the prefix thiol is seen in the name of an ion, it implies that a sulfur atom is present in the ion and that this sulfur atom actually replaced an oxygen atom that was initially present in the ion. E.g., in the ion thiocyanate and thiosulfate. Thiocyanate ion is gotten from the oxocyanate ion, while thiosulfate is believed to have been gotten from the sulfate ion, SO42-. Now, look at the oxygen atom present in the oxocyanate ion here. If this oxygen atom is replaced by sulfur, we get thiocyanate ion. While if the oxygen atom, one of the 4 oxygen atoms in the sulfate ion here, is replaced by a single sulfur atom, then we get 2 sulfur atoms and we have 3 oxygen atoms left to give us the thiosulfate ion. So that explains the word thiol found in the name of ions. It means it has a sulfur atom and that the sulfur atom has replaced an oxygen atom initially present in that ion.